Hi, everybody. Let's see you again. And let's start our lecture. Okay. So, 1 second. And now, what I may say, today in our lecture, we will continuing magnetic field sensors study. And let's start with this topic. So, let's start with variable differential transformation force. Just a coil with a movable core as displacement sensor, as you can see in this figure, shows strong non-linearity even when configured in parallel. A much better linearity we can obtain with a transformer or with a movable core, the linear variable differential transformer. As you can see here on the bottom as a LVDT abbreviation, a linear variable differential transformer. Figure A on the left upper corner, this slide, shows an linear variable differential transformer with one primary and one secondary coil. The coils have tapered windings in opposite directions. Without a paramagnetic core, the coils are only weakly coupled. The voltage on the primary coil gives only a small output voltage at the secondary coil. However, when a paramagnetic core with high permeability is inserted in the hollow cylinder, the coupling between the coils is much stronger at the position of the core. And the transformer ratio varies from high to low when the core moves from the left to right, according to the varying winding ratio at the core position. So, the output voltage varies with the core displacement. Are you agree? Although irregularities in the windings are smoothed out by the core, the linearity is not very high. A better construction is the one shown on figure B. You may see it on the right side of the top of this slide. This device consists of one primary coil and two secondary coils positioned symmetrically with respect to the primary and wound in an opposing direction. When the core is in its center position, the voltages over the secondary coils are equal, but with opposite polarity due to the winding direction, right? And the total output voltage of the two coils in series is 0. When the core shifts from its center position, the output voltages are not equal anymore. The one becomes higher while the others lower. The difference is a measure for the distance from the center position, as you can see from this slide. Note that the output amplitude is equal for positive and negative displacement. Information about the direction of displacement is given by the phase of the output signal. The phase with respect to the primary voltage is easy is a 0 or pi, depending on the direction of the displacement. The stroke of the construction in figure B is limited to about 1/3 of the total length. A shorter core would result in a much larger range, but at the expense of linearity. The solution is obtained by distribution of the primary and secondary windings over the sensor body is depicted on the figure C. You may see on the bottom part of this slide. The distribution is such tapered that the output amplitude varies linearly with the core displacement over a range about 80% of the length. End of stroke nonlinearity is further compensated for by additional turns at the extremity. The LVDT is operated with an AC voltage. Its amplitude and frequency can be chosen by user within a wide range. Typically, it's from 1 to 10 voltage and 50 Hz, maybe up to 10 kilohertz. Its intensity is expressed in millivolt output per volt for input and per meter for displacement as a units with meter. Users who wish to avoid the handling of AC signals, like amplitude and phase measurement, can choose the DC LVDT, but with built-in oscillator and phase-sensitive detector. You know, the both input supply voltage and output as a displacement signal are DC voltages. A stainless steel housing guarantees proper shielding against mechanical and chemical influences, as well as against electrical and magnetic interference. Special types withstand high pressure up to 200 bar or are radiation resistant. To further improve the performance, special constructions and compensation techniques have been developed. A self-compensating arrangement with two sets of secondary coils, and the two sets are exposed to the same environmental influences and excitation voltages, but they generate two outputs, a sum and a difference voltage. The ratio of the two is independent on common interferences, more or less similar to the post-processing method for a position-sensitive diode, or if you're using optical sensor. A 2D version of LVDT with a range of approximately near the 30 centimeter in two directions. A special design for very low temperature up to 70 Kelvin. To illustrate the quality of standard LVDT sensors, this table presents selected specifications of a typical commercial type, namely LVDT. The overview, this table, at the end of this section, lists some general characteristics of the LVDT. The rotational version of the LVDT is the rotational variable differential transform, RVDT, rotational variable differential transform. The principle of operation is the same as for the LVDT due to the particular configuration of the coil, and the rate is restricted to less than 180-degree rotation. Inductive sensors for the full range of 2 pi are the resolver and the synchro. These types are based on variable transformer as well, with fixed and rotating coils. The coupling between primary and secondary coils depends on the angle between the coils. The resolver, as you can see on the figure A, essentially consists of 2 fixed coils. Usually it's named as a stator, making angles of half pi, and 1 rotating coil, the rotor. The voltages across the primary coil have a phase difference of half pi radiation, and V1 proportional to V times cosine omega t, and the same V2 proportional to V times sine omega t respectively. You may see this expression on the bottom part of this slide. Both stator coils induce voltages in the rotor coil. The 2 induced voltages add up in the rotor. Assuming equal amplitudes of the stator voltages, the rotor voltage is expression as V3 in this expression. So, hence, the phase relative to B is equal to the geometric angle of the rotor, as you can see from figure B. The coefficient A in this equation accounts for the transfer between stator and rotor. Instead of supplying the input voltage to the stator coil, so-called stator supply mode, the input voltage can be supplied to the rotor coil as well. The rotor supply mode. In this case, the stator coils provide 2 output signals from which the mechanical angle can be derived. Multipole revolvers have 2 stator coils and 2 p-bound rotors. The output phase at the stator coils varies over a full period when the rotor rotates over an angle of 2 pi over p. So the resolution is increased by a factor p. Okay, let's go on. Configurations of these 3 stator coils are called synchros. The 3 coils make geometric angles of 120 degrees and are supplied with 3 sinusoidal voltages, which also have phase differences of 120 degrees. The principle is the same as for resolvers. Resolvers and synchros have a measurement range of 2 pi radian. Measurement frequencies are around 10 kilohertz. The performance is mainly limited by the readout electronics, in particular, the phase measurement security. The accuracy can be better than 0.001 radian. It's approximately 3 minutes of arc, or as we say, minar. Whereas a resolution down to 40 seconds of arc can be achieved. If you remember, 1 degree is 60 minutes of hour or 3600 seconds of hour. Okay? An analysis of the various kinds of error together with a compensation method to reduce errors. Other attempts to reduce errors are found in using a lookup table. So calibration is required, in which special electronics perform an accurate conversion from a resolver output to a DC signal with an error as low as 0.01 degree. A variation on the resolver is the inductor scene. Inductor scene, we discuss only the linear inductor scene here. The rotational version operates in the same way. The linear inductor scene, as you can see in this figure, consists of a fixed part, the ruler or scale, and a movable part, the slider. Both the ruler and the slider have Minder-shaped conducting strips on an isolating carrier, like a printed circuit board, and isolated from each other by a thin insulating layer. The ruler acts as one elongated pole. Its length determines the measurement range. The slider consists of two short coils with the same periodicity as that of the ruler. However, the geometric distance between the two parts of the slider is proportional n plus 1/4 of a geometric period p. The inductor C is activated in a similar way as the resolver. The sliders are supplied with AC current, currents I and I with half-pi phase difference. The ruler receives the sum of two induced voltages according to the equation you can see previously. Again, the amplitude of the output signal is almost independent of the slide position, and the phase is a measure for the displacement. Unlike the resolver, the inductor scene has no iron, so the operating frequency can be higher, up to about 150 kilograms. To measure absolute displacement over the total extent of the ruler, the system must keep track of the number of electrical periods that have passed. In this way, an almost infinite range can be achieved. The inductor scene is very suitable for accurate positioning in, for instance, LA. And this table compares major specifications of the various inductive sensors discussed in this part of lecture. A magnetostrictive or magnetoelastic or even elastomagnetic sensor is based on the change of the magnetic flux in a magnetic material due to deformation. Therefore, the effect is mainly used for force sensing. Basically, two different magnetoelastic sensor systems can be recognized: uni- and multi-directional. Sensors of the first type consist of a coil with usually cylindrical core from a suitable magnetostrictive material. as you can see on the figure A at the left part of this law. Upon compression of the core, the permeability changes, and so do the reluctance and the self-inductance, according to the empirical and linearized expression. And you can see here as for delta of the bottom, delta L over L. Proportional negative values, delta R sub M over R sub. Or expression as delta mu R over mu R, or simply proportional K times TK. The sensitivity is small, about 2 times 9 in power minus 9 square meters per meter. And furthermore, the output signal depends on the temperature and on the frequency and amplitude of the supply voltage. And the overall accuracy is several percent. Multi-directional devices use the effect that magnetic flux lines change direction when a force is applied. Such sensor can be used for the measurement of force or torque, and using special designs for both force and torque simultaneously. Figure B shows a magnetoelastic force sensor configured as a transformer. The core consists of a pile of ferromagnetic lamellae. Both primary and secondary coils have only a few turns positioned perpendicularly to each other. When no load is applied, the magnetic field aligns on the primary coil, as you can see in figure C, and do not cross the secondary coil, and hence the transfer is lost. Upon the applied force, the permeability of the magnetic material loses its isotrope, resulting in an asymmetric pattern of field lines, as you can see on figure G. In this situation, field lines can intersect the secondary coil, generating an output signal proportional to the force. In the so-called torque ductor, designed for contact-free torque measurement of an rotating axis, this axis itself acts as the magnetostrictive medium. It makes up the magnetic joint between the primary and the secondary coils of a transformer. The primary coil introduces a magnetic field in the axis. The transformer is configured in such a way that at zero torque, the transfer is 0 too. An applied torque results in torsional stress, as you can see in this figure, causing a change in direction of the field lines, according to the Villary effect. This, in turn, results an induced voltage in the secondary coil of the transformer, similar to the torque sensor in figure D. By a set of the magnetoelastic transducers, this proper configuring the magnetic force and the primary and secondary winding, a combined force and torque sensor can be realized with a reasonably small crosstalk between the two measurements. An alternative for the magnetostrictive method is stress-sensitive amorphous ribbon. When taped on the spark surface of an axis, the ribbon is stressed, becomes anisotropic, and exhibits magnetoelastic properties that can be used to measure torque similar to strain gauge. Magnetostriction can also be used for linear displacement sensing through use of a special design. One such design consists of a rod made up of a magnetostrictive material, the fixed part, as the body of a linear potentiometer. A movable coil surrounding the rod is connected to the part whose position or displacement has to be measured, so the viper of the potentiometer. The coil is activated by a short pulse, which generates an ultrasonic wave in the rod. The wave travels from the coil toward each of the ends of the rod, where ultrasonic receivers measure the travel time. Clearly, the position of the coil follows directly from the travel path of the two waves. Magnetostrictive related hysteresis limits the accuracy, but this can be reduced up to factor of 10 by a proper biasing in the magnetic material. And this section concludes with a linear induction type position sensor, of which the concept is shown in this figure. The structure is similar to the magnetostrictive sensor from the previous part of the lecture, and it consists of an elongated soft magnetic core and a magnet or activated coil. The latter moves along the core, similar to the viper of a potentiometer. At the position of the magnet, the core is locally saturated, so the permeability of the core at that position has a much lower value compared to the remainder of it. The total reluctance of the structure depends now on the position where the core is saturated. The magnet acts as a magnetic shortcut of the core. The position-dependent reluctance can be measured in various ways. This is accomplished by LVDT-like configuration with primary and secondary coils, and by a self-inductance measurement in differential configuration. In both these cases, the prototypes have a measurement stroke of about 20 centimeters. Now let's come to another part of our lecture called interface. You know, for properly interfacing an inductive or magnetic sensor, it is important to know the difference between the various sensor groups. And this figure presents an overview of the various sensing principles using magnetic or inductive sensing. Magnetic tau, the output of the magnetic sensor, varies with distance between sensor and magnet. Induction type, the moving magnet induces a voltage in a coil. The output is proportional to the relative velocity. Inductance type, in this case, the self-inductance of the coils varies with the position of the moving coil. Transformer type, in this case, the transformation ratio varies with the position of the moving coil. According to the type of sensor, an interface circuit has to be designed for the conversion of its output parameter into a voltage or current. Modern integrated magnetic field sensors have a built-in interface The output is a voltage or sometimes a current or a frequency proportional to the applied magnetic field. The output of an induction type sensor is a voltage which only needs to be amplified if the voltage level is too low. It should be pointed out that although the overall sensitivity is increased by the gain of the amplifier, the S/N ratio is decreased, or at best remains the same when the amplifier noise is small compared to the noise from the sound. The output quantity of an inductance sensor is a change in self-inductance. The conversion of these quantities into an electrical signal can be accomplished in similar ways as for capacitive sensor, as you can see in this figure on this slide. However, while capacitors behave as an almost ideal capacitor, this is not the same case for the coil. The wire resistance and the capacitance between the turns are usually not negligible, making the impedance of a coil differ from just a pure inductor. Most integrated interface circuits are based on a relaxation oscillator because of circuit simplicity. The relaxation oscillator generates a pulse or square-shaped periodical signal with a frequency determined by the value of the self-inductance of the sensor. Since the method is essentially analog, a high resolution can be achieved down to 50 nanometers. A completely different approach is given here, where the frequency-dependent transfer characteristic of a low-pass filter, including the sensor impedance, and is used to convert a change in self-inductance into a change in the output amplitude for the filter. Many sensors discussed in the previous sections are available together with interface circuits in one package. They provide output voltages suitable for a direct connection to an ADC, such as a with linear proportional Hall sensor, or standard 24-volt output for industrial programmable logical controllers, PLC. Some sensors, like the absolute Hall effect position sensors, have a communication bus, which can directly be interfaced to embedded electronics. On-axis rotary sensors, manufactured, for example, by AMS, have a serial peripheral interface communication bus, which facilitates calibration options for the end user, as well as a high resolution position output, directly suitable for further processing. The transformer-based sensors, as discussed earlier, are, however, a different and more difficult class of sensors to interface in the digital domain. Tailored solutions exist. Also, it might be useful to give an example of how to interface such sensor type, like synchro, using the Arduino board with only a few passive components. The example setup is shown in this slide. A synchro typically contains 3 state windings for a 3-phase excitation voltage. The phase of the rotor voltage changes according to the rotation angle. Many microcontroller boards, like the Arduino, do not have dedicated analog outputs, but can generate pulse width modulated signal based on internal times. When the pulse width modulated frequency is high enough compared to the highest frequency component of the generated signal, it is possible to generate analog-like signal by filtering. In the sketch interfacing example in this figure, the Arduino board generates 3 sine waves with phase differences of 120 degrees, which are used to power the 3 stator windings. The voltage at the rotor winding is sampled using one of the analog inputs using the standard ADC. Since this ADC cannot read negative voltages, the second connection of the rotor is biased with 2.5 volt offset using a voltage divider. When only the phase shift of the signal is detected, a digital input is enough for measuring the zero crossing. The analog output voltage can also be measured, and the phase of the signal can be determined, for example, by taking the arcsine of the signal voltage. In this slide, the synchronous stator windings are excited with 100 Hz sine wave. The PWM frequency, typically around 8 kHz, is filtered out using 3 passive low-pass filters consisting of a 1 kilo ohm resistor and a 1 microfarad capacitor. And this figure shows this voltage at 100 Hz. Inductive and magnetic sensors cover a wide application area. In mechatronics, they can be used to measure many quantities, linear and angular displacement, and their time derivatives, force, torque, and material properties. Eddy current sensing is also used to detect defects in metal structures or for quality monitoring in production. The magnetic displacement sensors in this section are based on a position-dependent magnetic field strength. The strength of a magnetic field originating from a permanent magnet or an activated coil depends on the distance from the magnetic source. And generally, the strength decreases with increasing distance from the source in a way that depends on the pattern of magnetic field lines, as represented in this slide. Magnetic field strength can be measured by any magnetic sensor. For instance, a cold plate, a flux gauge sensor, or a detection coil. The latter responds to fluctuating fields only. So in this case, the magnetic field must be generated by an AC activated coil. Displacement measurements using a magnet sensor pair have a limited range, a strong nonlinearity, depending on the relative movement, as you can see on the figure. Ferromagnetic construction parts in the neighborhood of the sensing system may disturb the field pattern. The major application, therefore, is as a proximity sensor or a switch. An important parameter is the switching distance. which depends on the mechanical layout of the sensor, but also on the dimensions and material of the moving part. In commercial systems, the switching point can be adjusted over a limited range by varying the sensitivity of the electronic interface, as you can see in this table. One range displacement measurement can be realized using permanently magnetized strips. And this figure shows some possible configuration. One option is a strip that is magnetized with alternating north and south poles. Look at the top of this slide, figure A. A magnetic field sensor moves along the strip like the slider in a potentiometer. Starting from a reference position, an electronic counter keeps track of the number of transitions from negative to positive sensor output, similar to the optical incremental encoder that will be discussed a bit later in optical sensors. These two sensors space n plus 1/4 over magnetic period, which can be as small as 200 micrometers. The direction of movement can be determined as well. The reference marks are not susceptible to magnetic fields. Advantages of this type of sensor are its robustness in unlimited. Robustness and corrosion resistance like strips of stainless steel. And you should know that the measurement range is usually unlimited. It is possible to attach a strip to carved surfaces as well. Attainable resolution is nearly half micrometer over a limited range. Maximum velocity of the sensor head is about 20 meters per second. Opposed to this multi-magnet single sensor system stands the multi-sensor simple magnet system based on the configuration on figure B. When the sensors are positioned in such a way that the sensitivity characteristics overlap, unique position measurement over a wide range is achieved, as you can see in figure C. Interpolation between two adjacent sensor positions provides accurate distance data. Absolute linear encoders using a special code and readout procedure is available, providing a measurement accuracy nearly ±5 micrometers and a resolution down to 1 nanometer over a range over 25 meters. The self-inductance of a coil not only depends on the lift-off distance to a conducting target, but also on the conductivity of the target, as you can see in this figure. This property is exploited to measure liquid level and liquid conductivity at the same time, using two coaxial coils located above the liquid. A model-based approach is followed to the infer both quantities from the frequency-dependent imaginary part of the impedance. The level and conductivity range are from 0 to 30 centimeters and from 4 to 10 respectively. As discussed previously in the section on resistive sensing, AMR sensors are frequently used to detect rotation and translation, usually in all robotic applications, using a combination of static magnets and sensors. Also, the sensitivity and linearity of Hall effect sensors is essentially small. Advancements in designing integrated versions, combining sensing, conditioning, calibration, and communication in a single chip have tuned Hall effect position sensor into the market as a viable alternative. A linear proportional Hall effect sensor, as you can see from this slide, in combination with static magnets, exhibits a strong linear behavior as shown in this figure, due to the inhomogeneity of the magnetic field. Therefore, they can be used primarily as switching type or limit type sensors. However, it is well possible to linearize this behavior, especially where space constraints are the most limiting factor. These sensors can still offer a reasonably accurate position reading. Humanoid robot finger designs, for example, frequently employ these sensors. Also, the sensor does not rely completely on the absolute value of the field strength provided by a single magnet. A homogeneous field generated by multiple magnets can be detected, shown in this figure in the central and right part. And a very accurate position reading can be achieved. Sensors in this category typically offer a resolution of 12 up to 16 bits. Eddy current sensors and other variable reductor sensors are suitable for testing the surface quality of metal objects. Cracks increase the resistance for eddy current. Object classification based on material properties, the sensor impedance, depends on the resistivity. And let's see this figure. So the contact-free distance measurement and even detection like holes, edges, and profiles in metal objects. An inductive tachometer consists of a toothed wheel fixed on the rotating shaft and an inductive measuring head positioned close to the circumference of the disc. Each time a tooth passes the sensor head, the interface electronics gets a count pulse. The pulse rate is related to the rotational speed of the shaft. Inductive tachometers are very robust and often applied in hazardous environments. A miniaturized version of this tachometer, flat foil, measures 1 up to 1 millimeter and has 10 turns only. An interface circuit converts a change in inductance due to a passive tooth of a gear wheel to a frequency change from 9 to 11.6 megahertz. And this sensor also allows analog distance measurements with 50 nanometer resolution over a half millimeter range. Although the working range of eddy current sensors is limited, the measurement range can be enlarged by mechanical reduction of the movement to be measured. As an example, this figure shows a configuration with an eccentric and two balanced eddy current sensor to measure rotation. In the neutral position on the left side, the distances x1 and x2 are equal. But when the bar rotates clockwise, x1 decreases, whereas x2 increases at the same time. Both the amount and the direction of the rotation are measured using very simple and robust sensors. In the eddy current angle sensor, the large range, it's equal 30 degrees, is obtained by a special mechanical construction. The rotating part has a symmetrical shape, turning in a coil that makes an angle with the axis. When a conductor moves in a magnetic field, eddy currents are induced, affecting the self-inductance of the coil that produces the magnetic field. This is the basic principle for a contact-free velocity or acceleration sensor. An alternative approach to measure velocity using eddy current sensors applied to rail vehicles. This method is based on correlation, the same as optical sensors and acoustic sensors. In this case, two eddy current sensors positioned about 10 centimeters above the rail track and with the fixed distance d apart pick up the irregularities of the rail. The rail clumps are actually detected. The cross-correlation function of the two signals shows a peak for a delay time equal to d over d. And in this case, the correlation function is periodic, but a special correlator is able to find the correct maximum value. In practice, a rail vehicle also makes common in vertical and sideways movement. A differential configuration of eddy current sensor is insensitive to such movement. The presence of capacitance and the skin effect make the impedance of an eddy current sensor frequency dependent. So the transfer characteristic contains information about not only the distance between the sensor and the target, like the lift off, but also the properties of the target, thickness and material. In general, the sensor can be modeled as a second-order system, of which the resonance frequency and the quality factor or damping are determined by the material properties, the thickness, and the lift force. And this makes eddy current sensing suitable for thickness measurement. For instance, of a non-conductive coating on a metal background or of conductive sheet for measuring conductivity and permeability, and for material identification, to mention just a few examples. Pressure is usually measured by an intermediate elastic element. Its deformation is proportional to the applied force of pressure. This deformation can be measured by an eddy current or variable reluctance sensor. This principle is demonstrated where the elastic element is a flat membrane. The deflection is sensed by a flat coil made on a PCB, and by force feedback using a sensing coil, the deflection is compensated. According to the general feedback principle explained in uncertainty aspect. Eddy current sensors are widely used for non-destructive testing of all kinds of products and materials. In this application, the object is scanned by moving one or more eddy current sensors over the area of interest. Surface irregularities are detected as an unwanted variation in distance of the object. Material defects like cracks and corrosion are detected based on a change in local conductivity or permeability. The simplest sensor is a flat coil, which is adequate, for instance, profile measurement. With an array of sensors, the scanning can be limited to just one direction, a useful solution when the resolution requirements are not very high. For the detection of more complicated structures like pipes, various other possible configurations have been proposed. A particular example is the use of eddy current sensing for metal tag recognition. The tags consist of a special flat metal pattern and are scanned with an eddy current sensor. In this case, a transmitter and receiver port. Flat-coil eddy current sensors are also suitable for imaging roughness and defects in metal surfaces. Either the object is moved along an array of eddy current sensors, or the test surface is scanned mechanically by a single sensor. The technique provides images with a spatial resolution down to 1 millimeter. Another method to detect defects in conductive structures is magnetic flux leakage. The principle of this technique is shown in this slide. The object under the test is magnetized by an external magnet. In the ideal case, the magnetic field is mainly located inside the object because of its high permeability compared to the surrounding air. In case of a surface defect, like hole and crack, the permeability at the location is low, and this causes the magnet flux to bulge out the material. And this leakage of the magnetic field can be measured by a magnetic sensor located just above the object surface. But you should note that the defects create field lines perpendicular to the surface, so sensing in this direction is recommended. With sensitive material sensor, it is possible to detect defects in the order of micrometers and even defects at the bottom side of, say, relatively thin, like several millimeters, plates or pipe walls. The magnetic flux leakage technique is still widely studied, aiming at the better resolution and a more accurate localization and characterization of defects. A promising technique is the pulse method that employs the dynamic behavior of the pulse response for the interpretation of the defect. For instance, it is shown that surface and subsurface defects give distinctive responses, and from the measured time to peak, the types of the defects can be reconstructed. Velocity and acceleration can be derived from position by taking the first and second derivative of the displacement signal. Real accelerometers make use of a seismic mass. When accelerated, the inertial force causes a deformation of an elastic element connected to the mass. The accelerometer is based on an LVDT with a magnetic fluid as movable force. The position of the ferrofluidic sphere is measured in the same way as is the core in a normal LVDT. In this sensor, the inertial force on the fluid is in equilibrium with the magnetic force. A magnetic fluid is also used in the tilt sensor. Here, the magnetic fluid acts as the support of a permanent magnet moving between two magnets located at both sides of the sensor housing. When tilted, the magnetic force is displaced over a distance determined by the tilt angle and the magnetic force. The position is measured by a differential pair of coils around the construction. Pressure and force are likewise determined by an elastic intermediate. The deformation or displacement of that element can be measured by an induction machine and is accomplished in various ways. For instance, the bending of a conductive membrane effect are reluctance of a magnetic circuit composed of this membrane and one or more coils. If the membrane is not conductive or ferromagnetic, small ferrite objects can be attached to both sides of the membrane, together with two coils forming a differential variable reluctance circuit. A strain sensor in which the coil itself acts as a deformating element. The coil is embedded in a flexible epoxy, and the change in coil shape causes its self-inductance to change. The combination of the differential sensitive magnetic field sensor and a permanent magnet that can rotate with respect to the sensor makes the basic structure of a magnetic angle sensor. The magnetic sensor can be of any type: an angular position sensor over the full 360 degrees based on a 3D integrated Hall sensor. Also, a 2D sensor would surface in the application, giving the sine and cosine of the angle. And the third sensitivity axis, measuring tilt angle, is used to compensate for the misalignment of the sensor relative to the magnet. The magnetic angular sensor is based on a different approach. The integrated device comprises four Hall sensors, a flux condensator, and an analog signal processing circuit. By special configuration of the Hall sensors and ratiometric principle of an almost linear output, near 1%, is realized over an angular range of 120 degrees. Large gap sensors have a high sensitivity and are therefore suitable for measuring the Earth's magnetic field, like as part of a compass. They are widely used for navigation purposes. Research is aiming at the increase of overall performance, a low price, and reduced dimension. Examples of such research work for satellite navigation, for spacecraft, and for land navigation too. And now we became a bit to the next topic of our lecture, called optical sensors. The majority of optical displacement sensors are based on variable reflection or transmission. Optical force sensors are derived from displacement sensors by adding one or more spring elements. Since light is a wave, one can also make use of travel time, phase shift, and interference. Most displacement and force sensing systems operating on optical principles consist of the three basic parts: a light source, a light sensor, and the transmitting medium. Often, auxiliaries are required, such as lenses, optical waveguides, mirrors, filters, polarizers, diaphragms, and choppers. An optical displacement sensor is constructed in such a manner that a change in distance between two sensor parts, or between one sensor part and a moving object, results in a change in transmission, reflection, absorption, scattering, or diffraction of a beam of light. The majority of optical displacement sensors are based on variable reflection, usually continuous, on transmission, usually on off. Other modalities are not often encountered in mechatronics. Optical force sensors are either derived from displacement sensors by adding one or more spring elements, or based on a change in parameters of suitable optical materials in particular fibers. Since light is a wave, one can also make use the travel time, phase shift, and interference. Optical fibers gain increasing interest as sensors next to their role as data transport medium. The transmission properties of such fibers can be modulated by various physical properties, for instance, temperature, humidity, bending, strain, and concentration of chemicals put in contact with the fiber. So you can refer at the literature on these specific subjects in internet and in library. And first, we discuss in this part of the lecture the main optical variables and parameters. Next, we review the properties of some electro-optical and optoelectrical components commonly used as measurement tools. The subsequent section deals with methods on how to build up sensing systems for the measurement of position and displacement using such components. This section also includes a discussion on optical encoders, like linear or angular sensors with binary output. Next section deals with some basic electronic interface signals. And finally, one part of next lecture will be devoted to the application of optical sensing systems in mechatronics. Next lecture will be optical sensors. I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye. See you.